recorded from this point on. Do it a bit more brightness. Wake everybody. Okay, let's look at the second question, which is part B. So determine the convergence of this series, the sum of 2 over n factorial, n equals 1 to infinity. Okay, so this is maybe, so it's not giving you much direction on this. I mean, you get a bit of a feeling when you look at that is, okay, the terms are it certainly passes the general term test. That would be the first thing to say. So this doesn't, let's say, this doesn't violate the general term test. Since the terms 2 over n factorial do converge to 0 as n goes to infinity. So it's not, so there's no conclusion we could draw from that, the fact that it passes the general term test, but it's just interesting to note. So it has a chance of converging. If at this stage we notice that the terms do not converge to 0, then that would be just the end of the discussion. You could definitely say then that the series diverge. But these terms are getting smaller and smaller and converging to 0, so it may converge. It has a, so it may converge. And then you kind of look at it and you think, well, it's n factorial at the bottom, and that's going to increase in value quite fast. Factorials, factorial 10, multiplying together all those numbers, take factorial 100, multiplying together all those numbers. So as n increases, the factorial does increase very fast. So that makes us think that these terms are going to decrease very fast, which suggests that it is going to converge. If you remember something like the harmonic series, the sum of 1 over n diverged because its terms didn't decrease fast enough. And the harmonic series was actually the kind of last, it was kind of the boundary between series of powers of n that converged and diverged. If it's the sum of 1 over n to any power strictly bigger than 1, it's going to converge. But when the power is 1 over n to the power 1, which is the sum of 1 over n, the harmonic series, that one diverges, and any time you have 1 over n to a power, and that power is less than 1, then that's also going to diverge. So the harmonic series is something of a dividing line. It's the most, yeah, it's what am I trying to say? It's a divergent series that only fairly diverges. Yeah, it's right on the boundary between convergent and divergent behavior. So if anything, if we see anything that behaves slightly better than the harmonic series, there's a good chance it's going to converge. Well, my point is this behaves like so much better than the harmonic series because the n factorials get very large very fast. So we think it converges. As 2 to the n factorial converges to 0 very fast. Okay? But that's very, that kind of argument, should convince, the defendant looks very innocent. Well, that doesn't mean he is innocent. They still could have done the crime. But it's circumstantial evidence. But what we need is we now need a test that's going to fully and rigorously justify this. So we look at the family of convergence tests for series, and we start to look at them and we think, well, which one might be a goer, which one might be a applicable to this? Which one might we be able to work out and get a conclusion for this series? And the one to use is the ratio test, actually. So we'll apply the ratio test. And remind yourself of the statement of the ratio test. Quickly. It's the ratio test. So the ratio test works by comparing the terms to themselves. You examine the rate at which the terms increase. And how you do that is you examine the limit of the ratio of the terms, an plus 1 over an. So there isn't a constant rate of increase of these terms. If there was a constant rate of increase, it would be a geometric series as a fixed constant rate of increase in terms, a fixed constant multiple from one term to the next. This isn't the case, but the ratio test is a kind of, it can detect tests that are acting like a geometric series test, like a geometric series. So what we do is we examine the ratio of consecutive terms and we take its limit. We see if there's any tendency or limiting behavior in the ratio of the terms, of neighboring terms. So we see if there's any limiting tendency in the scaling from one term to the next of the series. And the proof of this used a comparison test in combination with the geometric series test. Okay? And it said, well, if the tendency of the series we're looking at is like a geometric series test, so the limit of the ratio is L, and that L is strictly between 0 and 1, or strictly less than 1, then it is going to be a convergent series. If the limiting tendency of the ratio is bigger than 1, that means eventually the series we're looking at is going to be acting like a divergent geometric series. The scaling factor from one term to the next is going to eventually be greater than 1. Because the terms are going to be growing, so it won't be able to converge. So we're going to go for the application of the ratio test. So we let an equal the term and examine the limit as n goes to infinity of an plus 1 over an. So this is us having selected the ratio test. Now we go to operate it. So we examine the limit of the ratio consecutive terms. So an plus 1 is 2 over n plus 1 factorial. Dividing by an is the same as multiplying by the reciprocal. And this is also appropriate for this series because the factorials, when you take ratios of nearby factorials, they simplify, okay? Because most of the factors are the same. If they're neighboring or close, not that far away from each other, factorials, most of the terms are going to cancel and you just be left with a fixed number of factors behind. So that indeed happens here. In fact, this limit simplifies, this expression simplifies to 1 over n plus 1. Right? The 2's cancel and the factorial cancels, and it just leaves behind the factor of n plus 1 at the bottom. And this has a limit of 0. Okay? Because as n increases, that's going to get closer and closer to 0. So to operate our ratio test, then, we found this limit. This L is equal to 0. Certainly we do have an L in the correct range. So our series converges by the ratio test. Okay, does that throw up any questions or queries? anything related? Yes.
I don't really get how you, when you're applying the ratio terms, are you two over n plus one factorial two?
Yeah, so so I've got to divide an plus 1. So that means, so that is all in the subscript. So it's the n plus 1 term. It's the term that comes after an. So if an is 2 over n factorial, the term that comes after it is 2 over the factorial of n plus 1. Yeah? So that's so this here is the an plus 1. And this other bit here is the, well, I'm dividing by an, so I'm multiplying by 1 over an. Yeah? Can you see that? And then once you got them beside each other, the factorials, of course, the top factorial has, all of the factors of the top factorial are contained in the bottom factorial. So they cancel out, leaving behind just this first factor, n plus 1, that appears in the bottom factorial. Remember, the factorial of n plus 1 is n plus 1 times n minus 1, all the way down to 1. So this whole thing stretch here from n down to 1 is n factorial. So that's how that's important. Is that okay? Yeah?
Could we have used the comparison test with 1 over n squared?
Could we use a comparison test with 1 over n squared? That's a good question. So the series sum of 1 over n squared is convergent. Certainly. So we'll be looking to show that the term of our series is 2 over n factorial. Is it less than 1 over n squared, or, well, we can allow ourselves to use, if it's helpful, any multiple of 1 over n squared. That would still be a convergent series. Question mark, can we establish an inequality like this? Well, 2 over n factorial is 2 over 1 by 2 by 3 by n minus 1 by n. And can we say that this is less than or equal to alpha over n squared? I'm pretty sure we can. We just have to be careful about, there might be some early values of n for which it's not true, maybe. Sorry?
Did you say it's relatively weak about the tables?
Yeah. So it may be that there's some small values of n for which this isn't true, because, for instance, 3 factorial is, so what I want to, so if I want to show this is less than this, I have to be sure that this denominator is bigger than that denominator. Yeah. If the denominator is bigger than the fraction is small. And the only thing is, for some of the early values, it's not quite true, because 3 factorial is 6. 3 squared is 9. 6 is still less than 9. But then you go to 4 factorial. 4 factorial is 24. 4 squared is 16. So you've already overtaken the 2 there. So, well, we can say for every n bigger than or equal to 4, that implies that n factorial is strictly bigger than n squared. You happy with that? That's correct? Yeah. For n bigger or equal to 4, n factorial is bigger than n squared, so 2 over n factorial will be less than 2 over n squared. Okay. 4n bigger than or equal to 4. So yeah, you're correct. So this is the correct comparison to achieve in order to conclude convergence. And your remark about tails is also Correct. So by the standard comparison test, we can say that the series, the sum from n equals 4 to infinity of 2 over n factorial is also convergent. Since the sum from n equals 4 to infinity of 1 over n squared is 2 over n squared. Now this isn't the series we were originally presented with because it's lost the first few terms, but that makes absolutely no difference to convergence, because if this bit converges, this is the infinite tail of the series. All that's missing is the first few terms, and they just have some fixed constant value. So if this series is summing to, or is approaching a limiting sum as it develops, well, so will the series if we just add on the first few terms that we've missed out. So that implies that when you sum it from 1 to infinity, also converges. Because convergence isn't affected by what goes on in a few terms at the beginning of the series. It's all about what happens in the infinite tail of the series. In a certain infinite, so this is an infinite tail of the series. We've lost a few terms off the head. We've lost the n equals 1, 2, and 3 terms. So this is an infinite tail of the series beginning with 4. If that's convergent, so would the original series. If this was divergent, so would the original series. You can't fix divergence by just adding on a finite number of terms or subtracting a finite number of terms. Because it diverges because it grows without bound, so adding in a little finite correction to it is not going to stop that happening. Okay, that's good. And again, that's an application where you can often get more than one of the tests to work for any given series. And for tackling an unfamiliar series that's presented to you with no guidance, it can sometimes be a bit of a trial and error process to try one test, and maybe you won't be able to make one test to work on it. There might be a more appropriate test which falls out easier when you try to apply that. Yes, question?
In those tests, speed equally acceptable or not?
Oh, absolutely. Yeah, absolutely.
They wouldn't prefer one or the
Yeah. Unless there's a specific direction that says use the ratio test on this, then you should respect that. But if it's just examine this and decide, determine whether it converges or not, both would be equally fine. I think the ratio test does spring more to mind because of the presence of the factorial, and because factorials do cancel down so easily when you put them in ratio to one another. Oops. Okay, let's flip back to the exam. So that was what was that? That was one part B. So the rest of question 1 is from some of the second term stuff that we're going to be doing. And then Saeed has a compulsory, so that question 1 is compulsory on the exam. Last year's exam, everyone had to do it. Question 2, covering Saeed's material, is also compulsory. And then there were 6 questions in section B. And you have to make up a total of 5 questions. So you've got your 2 compulsory questions from section A, everyone has to do. And then you can choose any 3 questions from the 6 questions in section B. It's these 6 optional questions. They're all worth the same number of marks. And in this first one, 3 part A, B, actually all of these we can look at. The middle one, section B, we kind of considered yesterday because it was featured in the multiple choice question test. You were presented with 4 plausible looking versions of applying the standard comparison test to that series, but only one of them was actually correct. You have to identify that. So maybe let's do part C first, just to go to the more interesting things. And maybe I'll show you part D again, but using the limit comparison test. So in question C, still from the same exam, presented with a series here, sum of n equals 1 up to infinity, 2 over n squared is 2n. And you're asked to, what are you asked to do? Find the value of the series by using the partial fractions expansion of the term, examining the telescoping nature of the partial sums of the series. No. So, okay, let's do this. So remember, at the very beginning of the series chapter, we defined what this notation even means, okay? Because it's a bit paradoxical to add up an infinite number of things. But really, strictly speaking, we're taking the limit of the sequence of partial sums. So the series in the brackets now, there's no funny conceptual issues here because it's just a sum of a finite number of terms. Okay, it can be very large, of course, but there's nothing problematic about this sum here. And we're taking the limit of this sequence of sums. The limit as k goes to infinity of this. And there's something about the structure of this term that makes it particularly convenient to analyze, and that will allow us to calculate this value exactly, calculate the value of this limit exactly. So we seek we get the partial fraction expansion of this. Of the term. The term is 2 over n squared plus 2n. You factorize the denominator. That denominator factorizes nicely. And so what we expect is to find this as some constant over n plus some constant over n plus 2. So this is the type of expansion expected. The reason this is because it's just two linear factors here, two order 1 factors. They're not repeated, so we just need two fractions. It's a constant over the first factor and a constant over the second factor. So that's going to be true for some alpha beta yet to be determined. If the factorization was a bit more complicated, if one of these factors was repeated, it appeared to higher powers. For instance, if the n plus 2 appeared cubed, then you need three fractions for it. You need something over n plus 2, something over n plus 2 squared, something over n plus 2 all cubed. Okay? You need a series of fractions building up to the final multiplicity of that factor involved. And if you ever encounter factors here which are order 2, which are irreducible quadratic factors, then they'll appear here in the partial fraction expansion, but their numerators should be order 1, something times n plus sn. But this is about as simple as these partial fraction expansions would be. And then the normal, well, I mean, you might have already spotted what the values for alpha and beta should be. It's not too hard here. They have to have values that will cancel out the n's when you form this together again, and will end up giving you value 2. But there is a kind of fixed procedure you can go through to determine it, and that's to multiply, to add together the two fractions, which involves putting it over the same common denominator that we started from, and just tracking where the alpha and beta go. So the alpha has to multiply n plus 2, the beta has to multiply n. So it's just the rules for adding symbolic fractions you're familiar with. Now these two fractions are the same, they've got the same denominator, so they must have the same numerators. Just to get a clear view on this numerator, it's alpha plus beta times n plus 2 alpha. And this has to equal 2, But remember, it has to equal 2 for all n bigger than or equal to 1. So how can a polynomial in n be equal to a constant? Generally, it wouldn't be. If you've got a polynomial in n, it changes value as n changes, whereas 2 doesn't. 2 stays fixed at 2. So the only way this can be, and this is a principle about comparing polynomials, is that two polynomials are equal as functions. Okay? Because it's not just some particular values of these two are equal, it's they're equal all the time. Two polynomials are equal as functions only when they have equal corresponding coefficients. So that the constant coefficients of these two polynomials must be the same, and the n coefficients must be the same. Now we don't see an n coefficient up here because really the n has a coefficient of 0 in that numerator at the top. You can't see it because it's multiplied by 0. Whereas the coefficient down here is alpha plus b. So we can say comparing numerators in these fractions, these are this one and that one, comparing the numerators in those fractions, they must be the same. So this implies that alpha plus beta equals 0 and 2 alpha equals 2, and that's not too hard to solve. Alpha must be 1 and beta must be minus 1. Okay. But in general, at this stage, you get some system of linear equations in the coefficients in expansion. So if there were more of them or harder, you might have to default to Gaussian elimination, your row reduction algorithm that can always solve those systems. Okay. But here, the solution just pops out really. Alpha has to be 1 and beta has to be minus 1. So returning to our series, the sum of our series, by definition, is the limit as k goes to infinity of the sum from n equals 1 up to k. But now I'll use the partial fraction expansion. It's 1 over n minus 1 over n plus 2. So these things. And okay, these two fractions have the same numerator. Well, except one is positive and one is negative. One is 1, one is minus 1. And their denominators are just shifted apart by 2. So that means all these positive terms, 1 over n, all of them get cancelled by an earlier negative term. Positive fractions get cancelled with earlier negative fractions. Or in other words, the negative fractions cancel with later positive fractions. So in here, from here, you can see that positive fractions 1 over n will cancel with earlier negative 1 over n plus 2's. By earlier, I mean that, if you've got a quarter 1 over 4, you need to take the n equals 2 version of this. 1 over 2 plus 2. That gives you minus 1 over 4. That's going to cancel with the plus over. So positive fractions cancel with earlier negative fractions. But that means there are some left over because the positive fractions at the beginning don't have earlier negative versions to cancel against. Okay? Because there is no term where n is equal to minus 1. There is no term where n is equal to 0 to reduce the minus 1 to minus a half. Okay? Because the counting only starts at 1, n equals 1. And similarly, the negative fractions that appear at the end, when n is equal to k minus 1, and when n is equal to k, they don't cancel either because there are no later positive fractions. Because there is no positive fraction when n is equal to k plus 1 to cancel with this minus 1 over k plus 1 because the sum only goes up to n plus k. But everything else cancels. Okay? When you get this cancellation by terms that are out of phase like that, everything cancels except for some stuff at the beginning and some stuff at the end. But this is just a linear combination of simple enough sequence terms. Two of them are constant, so they don't go anywhere, they're fixed values. But these two have a k in the denominator, so as k goes to infinity, they're going to converge to 0. But really what we're doing here is we're using the algebra of limits theorem for sequences, so to justify it like this. The algebra of limits theorem. And the fact that 1 over k plus 1 and 1 over k plus 2 both go to 0. K goes to infinity. So this 3 over 2, this is the sum of the infinite series. Okay? So that was the overall instruction. Determine, find the value of this series. So there it is. Okay, do you see how I've tried to explain all the steps I've been doing there and justified the key steps where needed? In fact, I didn't write it down, but this is just by the definition. This very first one is just by the definition of an infinite series. That's what we mean by an infinite series. It's the limit of the sequence of partial sums. Does that throw up any queries or anything you'd like to ask for clarification? Okay, I might leave it there actually for this morning. So you'll have your tutorial either later today or tomorrow. I think the tutorials are going to look at first mock tests and any other questions you have, any other things you'd like to do. Next Wednesday, remember we're having our test. The details are there. I'll put the second mock up now later today. So look forward to seeing you all there. Please arrive on time, the correct time. And of course, there's no lectures taking place next Wednesday. Both of the sessions are used for the test. So don't turn up expecting a lecture. Turn up expecting